Hi there. It was brought to my attention tonight by an individual in the class that when you came to question number 3 on the Calc sense, probably 25% of you were probably able to do that question, and the other 75% went like, wait, what? What happened there? So I wanted to really quickly go over this. If you don't recall this lesson, that would be because it was on March 9th, 2020. If you're wondering why that date might mean something, I would simply point out that that was the first day in which we were no longer able to go back to school. It was the Monday of finals week, where 3 of our 4 classes from the last term were going to actually learn this topic. So for now, I just want to quickly go over what it is, where it comes from, and how it works, and how it's similar to what you knew before. It's not likely that this is going to be an AP test topic, but at the same time, we can at least hit it and make sure you've at least seen it once. And you can answer that question on the Calc sense. And I have 2 phones on my pocket for some reason. So in any event, what we have here is we have a derivative of an integral. So I'm guessing that most of you probably put something like this as your final answer. Because what we talked about in the past was the idea that when you take the derivative of an integral, those are inverse operations, so they undo each other. It's a pretty sensible thing. The only problem here is, in this case, we don't have an x as our upper limit of integration. We have an x squared. And you might not be clear right off the bat what it is you do in that situation. So let me just kind of walk you through the way this works by going back to what we did before. So let's take, for instance, this problem that we're looking at here. Let's say we want to evaluate this, but instead of having an x, let's give it an x squared. Or instead of having an x squared, let's give it an x. So if that was the case, if you wanted to kind of visualize this, if you didn't remember that, of course, this is just equal to the integrand, but with the x substituted in. So if you want to see where that comes from, and I'll do it quickly, the idea is we're taking the derivative of this integral. Well, the problem with this integral is we don't know what function has this derivative because there probably isn't really one anyway. So what I'm going to do is I'm going to create a function. I'm going to call it capital F. I'm going to say that that function capital F has derivatives square root of secant of t plus 1. So that way we start there. The idea is that our integral, which runs from 42 to now x because we changed it, is going to be the integral of capital F prime of t dt. If we use the fundamental theorem of calculus, we just have to anti-differentiate that function, which would get us, of course, capital F of t, and we'd evaluate it from 42 to x. From there, we know that the fundamental theorem of calculus says that's equal to capital F of x minus capital F of 42. But keep in mind, we still need to differentiate this expression to finish this off. When we differentiate the first term, we just get capital F prime of x. When we differentiate the second term, that f of 42, we've plugged a number into a function, which makes it a constant. So this then becomes just 0. But there's something more to this, because capital F prime of x is just that expression, except with an x in it. So in this case, actually I'll underline it in a different color, this expression becomes capital F prime of x, which is just the square root of secant of t plus 1. Nope, excuse me, x plus 1. Yeah, that's what I get for doing videos at 9 late o'clock. Okay, so there it is. So basically it undoes the integral and it leaves us the integrand. The only difference is there's an x plugged in. So this is exactly the same thing that's going to happen on the next problem except for one change. Because of the fact that we have that x squared, this is going to work in a slightly different way. Because suddenly we're not going to be introducing an x into our problem, we're going to be introducing an x squared. So here's what this would look like. We can basically keep the exact same work as before. I'm going to pretend there's a function, I'll call it capital F prime of t. And that capital F prime of t is going to be equal to the square root of secant of t plus 1. So we're just making it up because we don't know what it is. We don't need to know. So in here then, we will be taking the derivative of our integral, which runs from 42 to x squared, of what we're now calling capital F prime of t dt. Following the same pattern as before, we'll use the fundamental theorem of calculus. That becomes capital F, of t, and we'll evaluate it from 42 to x squared. And sorry, I meant to do all the x squareds in green. I apologize. That was something that I agreed to in my head. There we go. Okay, trying to emphasize where it's at. So then what's this equal to? Well, it's still going to be a derivative. We just have to get there. This will be capital F of x squared, and then minus capital F of 42. So at this point, we're ready to differentiate. We're going to take the derivative of this puppy. I was going to say, don't differentiate puppies, but I don't know what they're going to do. People love puppies. I love a puppy. So from here, we've got this derivative to take, and when we take the derivative once more of f of 42, of course that derivative is going to be 0 because it's a constant. So this will be something minus 0. The big difference here, though, is when we differentiate capital F of x squared, now that requires the chain rule, because we have x squared on the inside. We didn't think about it that way, but before we had x in there, and the derivative of x is 1. So it's kind of like it doesn't even matter. It's like the perfect chain rule situation. Here we have to deal with it. So the derivative of f of x squared is, of course, going to be capital F prime of x squared. But then because of the chain rule, we need to multiply on the outside by the derivative of x squared, which is in this case 2x. So where that leaves us is, of course, we don't need that minus 0 at all. But now we just need to make our substitution, because it says right up here, capital F prime of t is that secant thing, and we have an f prime right down here. The only difference is we've got x squared plugged in. So what does this come out to be equal to? Of course, we have that derivative of the inside, 2x. For our function, we have the square root of secant of x squared, or of what would be normally t or x squared, or t or x plus 1. We're going to plug in x squared. And there is where the answer came from. Now that I got it, so there is our answer. Now that looked like a lot of work to build up this idea, and the truth is this is one of the crunchiest looking things in calculus, but it's actually super clean and easy to work with. So the last things I'm going to do here is I'm going to define it once and state what's called the second fundamental theorem, and then I'll show you one more problem just to show you how fast it can go, because it's super clean. So here is the statement of what's called the second fundamental theorem. If you take the derivative with respect to x of an integral, and we'll just call the inside, I'll call it capital H of t, dt. And then we'll have two limits of integration up here. I'll call them f of x as the lower one, and g of x as the upper one. What this is equal to is going to be the same as before. So ignore those limits of integration for a second. When you differentiate an integral, those two operations undo one another. So we're still going to get h of something minus h of something. Notice I'm leaving some space, but yes. So that comes out no matter what. That's the structure of derivative and integrals being inverse operations. The difference is here, instead of plugging in x and 42 and then differentiating, here we're going to end up plugging in two different functions. So we'll have g of x and f of x in there. But when we do that step that requires the derivative of that fundamental theorem result, then we end up using the chain rule. So we multiply on the outside by g prime of x, multiply on the outside by f prime of x. Those last two steps right there are purely the result of the chain rule. And now just because it's the chain rule doesn't mean you actually have to do the chain rule. You just think it and remember that it's there, and you get your result. This is called the second fundamental theorem of calculus. And since it's on the first page, I'm just going to write it this way. So this is the other guy. This is the one that's, people don't like so much. Probably because it looks so complicated. So in any event, there it is. There's the statement. If you want to memorize such a statement, I think it's easier just to remember where it came from, but, do you. So as I said, I did want to do one more problem just to kind of illustrate that it's there. In this case, I'm going to pick ones out that are a little more complicated. Let's go e to the x, and ln of x. So our integral, or our integrand, is going to have, let's go with, I just did secant, let's go cosine of t to the 42nd power dt. And then, of course, we want to take its derivative. No, I can't do it. Close enough. So we want to differentiate this integral expression. So in order to do this, if you wanted to go through it the long way, that's great. I sort of think it through that way in my head. But the truth is, I can do this problem in under 20 seconds. The reason is, I just apply this thing called the second fundamental theorem. So again, it's how I narrate this through that would be the best demonstration you can get. So what do? First, I realize that the derivative and the integral are going to undo one another. Maybe not perfectly, but definitely undo one another, which is going to give us that inside structure. So stuff like this and stuff like this. And again, this isn't perfect, but close enough. So there's our stuff. Second, I've got to plug in those limits of integration, because that's going to happen through the fundamental theorem of calculus. We plug in the limits of integration and evaluate. So in here, I'm going to have the ln of x, and on the other one, I'm going to have e to the x. Last but not least, because when we plug those in, we then take the derivative afterwards, that produces the need for a chain rule. So on the outside, we'll have the ln of x prime, and on the other one, we'll have e to the x prime. And of course, from there, it's just a matter of evaluating it. This is 1 over x cosine of, it's kind of annoying to write, sorry, ln of x to the 42nd power. And then that second one is going to be minus, and it'll be the derivative of e to the x is e to the x, and then cosine of e to the x to the 42nd power. And there is our result. So truthfully, if you knew the derivatives, you don't even have to write out this kind of intermediate step. This is just me being super careful. Truth is, you can jump right to the answer. There's no work that's required here, just some thinking about where this came from. So again, it's not perfect. This is just kind of a quick lesson to cover for the fact that March 9th never existed as far as calculus lessons. If you're really interested in this topic, which don't personally think of it as the most interesting topic in the world, then hey, more power to you. The full problem set and video solutions are in the Calculus AB Google Drive, so be my guest and take a look if you'd like to. But if not, as I said, this isn't likely to show up on the AP exam, but it's definitely something that's worth taking a few moments to look at. And hopefully that was just enough to give you some context and background and stuff that you do know, as well as just enough thrust to move you forward through the problems. So with any event, thanks for watching and have a great night. And thanks to Harsh for asking about this.